Welcome to AI Explains. Today we're taking a deep dive into the landmark 2016 LIGO Physical Review Letters paper.
Right, the one titled Observation of Gravitational Waves from a Binary Black Hole Merger.
Yeah, it's quite a mouthful. But our mission for this deep dive is to decode this monumental physics breakthrough into simple, everyday terms.
Exactly. No science degree required.
Right, so that you, the listener, can easily grasp it even if you are completely unfamiliar with this field.
It's surprisingly intuitive once you break it down.
It really is. Okay, let's unpack this. Imagine two invisible giants out in the universe crashing into each other so violently that they literally send physical ripples through the fabric of space itself.
I mean, it sounds like pure science fiction, doesn't it?
Totally.
But it's very real. To truly appreciate this, you have to go all the way back to 1916. That was the year Albert Einstein mathematically predicted that these ripples, these gravitational waves, should exist.
Right, but he thought they'd be incredibly faint, didn't he? Like almost impossible to actually detect.
Exactly. For almost a century, they remained just a mathematical theory on a chalkboard. Humanity had to wait nearly 100 years to build technology sensitive enough to catch them.
100 years of waiting.
Yes, until finally, on September 14th, 2015, we actually heard them.
Wow.
What's fascinating here is the sheer colossal scale of the event. We are talking about two black holes orbiting each other. One was 36 times the mass of our sun.
That is huge.
And the other was 29 times the mass of our sun. They just spun closer and closer until they merged.
And the math behind that merger is the real aha moment for me. If you do the simple addition, 36 plus 29 equals 65.
Right.
Yet the paper notes the final black hole was only 62 times the mass of our sun. So where did those three missing solar masses go?
They didn't just vanish. In a fraction of a second, the mass of 3 entire suns was instantly converted into pure gravitational wave energy.
3 entire suns turned into energy in a split second. My brain almost rejects that level of power.
It is the most powerful event humanity has ever detected.
Here's where it gets really interesting, catching that energy. I know scientists use the advanced LIGO detectors in Washington and Louisiana.
Yes, the twin facilities.
Which are essentially these massive 4-kilometer-long L-shaped tubes. But how do giant empty tubes actually capture invisible space ripples?
Well, it comes down to lasers. Because they are built in an L shape, as a gravitational wave passes through Earth, it physically stretches space in one direction.
And squeezes it in the other.
Precisely. And because of that tiny change in distance, the lasers bouncing back and forth inside the tubes arrive back at the sensors at slightly different times.
And the change in distance they measured was smaller than a single proton over 4 kilometers.
An unbelievable level of precision.
It really is.
And it gave us incredible visual data. In the spectrogram images from the paper, this massive cosmic collision showed up as just a tiny 0.2-second chirp.
Just a chirp.
Just a chirp. It was a quick upward sweep from 35 to 250 hertz, perfectly matching the final moments of the black hole spinning wildly before impact.
So what does this all mean? Why should you care about a tiny 0.2-second blip on a graph?
It's the ultimate question.
Because before this discovery, humanity could only see the universe using light. Visible light, X-rays, or radio waves. This discovery gave us an entirely new sense.
We can now listen to gravity.
Yes, for the very first time.
If we connect this to the bigger picture, this firmly proves that Einstein's theories of general relativity hold up perfectly, even in the absolute most extreme, chaotic environments in the universe.
But completely opens up a new frontier for exploration.
It does. And this raises an important question, something built on a specific detail at the end of the source paper, the stochastic background.
The cosmic static.
Exactly. If countless distant, unresolved black hole mergers are constantly creating a background hum of gravitational waves.
All across the universe?
Yes. What unseen chapters of cosmic history will we decode once our technology is sensitive enough to tune into that cosmic static?